All right, let's go and get started. Let's see, let me go ahead and get the sign-in sheet passed around. So, as you remember, last time we sort of lost our video for the Shear design lecture. So after finite elements last night, I sort of repeated the example and recorded it last night, so it's on the playlist now. So what we're going to do today is do another example that is about the same, but it's a little more involved and a little more complicated, solely because the loading's different. So I'm actually going to make you all draw some shear diagrams and do a little bit of thinking about some of the design. Now, I'm going to, sort of skip over a lot of this stuff that we did in terms of procedure, or deriving the procedure, and just really briefly re-explain, the procedure, and then we'll go ahead and get into this example. So we have to construct our shear diagram, which we're going to do today for the example, the next example, but I'm probably not going to do it as neatly like I was using the straight line features in Smartboard and what have you. I'm probably not going to do that. I'm just going to sketch it out. Excuse me. But we have to identify our three regions where stirrups are required, where the concrete carries the shear, and where we don't need stirrups at all. We calculate our S value based on VU star to get our design started. Usually begin our first stirrup at around 2 inches or half that first increment, whatever makes sense. And then continue from there. We can improve that design using an additional stirrup spacing of S equals S max, which is the minimum of those two. Refine that design a little bit, and then as a final step, make sure you check this. We're checking that because this S max 1 is contingent based off of that requirement, so it usually never becomes a problem, but just to do your diligence, you need to go through and do it. Now here's example 12 that we did, and this was a uniformly distributed load. The shear design is pretty straightforward from an analysis standpoint because it's about the simplest shear diagram that we construct. This one, not so much. Now we have a beam where there's a little more going on. We have a distributed load of 4 kips per foot that includes the self-weight, but we also have point loads of 20 kips acting at quarter points along the span. So for this beam, what I want to do is do the same process, but now it got a little muddier and a little more complicated. But again, not something that you shouldn't be able to handle. Dimensions changed a little bit. We got 3 KSI concrete now, but in the end, should be fairly straightforward. All right. One other thing I'll point out, I did sort of put example 12 and finish it and put it in my little notebook or what have you. So it's on YouTube now, so if anybody needs to review it. Excuse me. Okay. All right. Okay, so let's look at some beam parameters first, make sure we're all on the same page. Okay, so we have FC prime is what, 3 KSI? Now it's normal weight concrete, so what does that mean? There we go. We've got FY for the stirrups, it's going to be 60 KSI. For the beam dimensions, we have B is 10 inches. Oh, what happened there? 20 inches for D. And the length is 24 feet or 288 inches. And we have number 3 U-shaped stirrup. So what's that mean? times all right. Make sense? Okay. So step one. Let's bring it back to last semester. Yes. After break. It'll be after break. My guess is, and I haven't decided about the steel exam, I think it's just going to be bolts and welds. And I'll say this, the steel exam is probably going to come first. So, but I'm not 100% on the dates. I'll let you know. I'll have a more codified schedule when you all come back. Sound good? All right. Okay, and what's that distributed load equal to? Y'all have it in front of you. I'm making y'all. What's that? And then there's also, let's see, a point load about right here. Then a point load about right here. And they are 20. And I'm writing the PU and the WUs to indicate that they're factored. Okay? Now that's going to indicate some reaction right here. And then some distances. Six foot, that makes that 12 foot, makes that 6 foot. All right. How are we going to compute R? Now, you all should be able to do this from what we did in structural analysis. Some moments at the left support to compute the R on the right support. But by observation, everything is symmetric, right? So why don't I do this? Why don't I say this? I say it's 20 kips times 2 plus 4 kips per foot times 24 feet. That would be the total load on the whole beam, right? Cut it in half. Wouldn't that be the reaction on each end? Are you okay with that? So that is what? $68 kips. Now, any questions? Now, before I start drawing a super detailed shear diagram, let's see if you all remember this. Let's go back. Let's just sort of sketch one out, make sure we know what it's going to look like. So what do? I start on the very left and I go up to what? Then what do? Slope down. 4 kips per foot, so that's how much? 24 kips? So if I'm at 68 and I go down 24, that puts me where? See how we're doing this? Bringing it back, right? Y'all remember that, right? Am I missing any arrows or anything? Okay. Is everybody okay with this? Now, I've got two questions for you. Now, before I ask those, when we do our design, it really doesn't, shear, it really doesn't matter about your sign convention. I can look to the left or look to the right, and as long as I'm taking everything as absolute values, it really doesn't matter for the purposes of shear design here, so I'm not going to really consider that. But I want to do two things. Number one, watch this. Let's see if you all can tell me this. If I were to take this line and extend it, what would that value be right there? If this is a straight line, right? If I just, what would the value be right here? Say it again. 48, right? Does that make sense? Is everybody okay with that? Okay. Now, that's number one. Now, number two, I've got a lot of, what is it, these diagonal lines. What is the slope of those diagonal lines? Say it again. It's 4. Well, technically not 4, it's -4 because it's going down. The slope of the shear diagram is equal to the magnitude of the load. I think what did we do right here? We went down how much? 4 kips per foot. What's so funny? This is a little more abstract, I'll give you that, but you should remember that. I mean, even if you don't remember, we just did it. So what I'm going to do is this. I'm going to call this region 1 and call this region 2. And I'm going to say, recall that the slope of the shear diagram is the loads, so therefore slope is -4 kips per foot. So what I'm going to do is this. I'm going to say for region 1, I'm going to say that the shear as a function of x is 68 minus 4 kips per foot times x. And for region 2, I'm going to say it's 48 kips minus, kip per foot. Now, how did I just pull those numbers out of thin air? What's the equation of a line? mx plus b. What is m? It's the slope of that line, which is -4. So mx plus b. Okay? Well, what's b? It's the y-intercept. For the first region, where do we cross the y-axis? 68. Where do we cross it here? 48. Does that make sense? So I propose to you that this first region, this equation, is going to be valid from 0 feet to 6 feet. And this is from 6 feet to 12 feet. Now, technically, we could take that and go on to 18, but we really only care about up to midspan. Does that make sense? All right. All right. Does everybody have what they need here? No? You good? Might break a rule and use the board here for a second just because I don't want to keep hopping back and forth, but we'll see. All right. We're on example 13. Okay. Now, to define our shear diagram, we've got the loads, but we want to indicate regions of interest. So we need to look at the concrete. So let's look at the concrete capacity. How do we calculate the concrete capacity? There we go. There we go. You put in PSI, you get out PSI. What is it, 10 inches and 20 inches? There we go. And 3,000, right? Sound good? All right, okay. So plug and chug, and you should get 21,909 what? If I just plug those numbers in, what's the units? No. PSI for the square root of FC prime, but PSI times what? There we go, pounds. We're talking about a shear capacity. That better be a force. So 21.909 kips. Then I'm going to go ahead and calculate phi VC. What's phi? And then plug and chug, and that gives you and then remember we calculate half of phi VC. Which is all right. Is everybody okay with what we just did? Everybody okay? All right. Now, let's look at some important values. Now, before I start calculating these important values, I know I may be a little redundant, but I'm going to do it again. I'm going to say that VU of X I'm going to say it equals 68 kips minus that, or 48 kips. And this first equation is for 0 to 6 feet and 6 feet to 12 feet. Would you all agree with that? Everybody okay with that? Okay, now, let me ask you this. Let's start off with VU star. Let's start off with VU star. So VU V star. Remember, that is our beginning value that we use for design. Remember, we're allowed to cut that shear diagram off D away from the support. So what's D for this beam? 20 what? Inches. So if I want to determine the shear at x equals D, do I use the top expression or the bottom expression? There we go. Okay. Making sure we're using our noggins. Anybody got a problem with that? There we go. So plug and chug, and that gives you that. Everybody okay with that? Now we're also going to need to determine the x values at phi VC and the x values at half of phi VC. Excuse me. Okay, so let me ask you a question. What is phi VC and what's phi VC? 16.432, right? And half of phi VC is 8.216. Now, these equations, it's not as simple to tell, but let's go back to the previous slide and let's look at this. This is our shear diagram, right? Now we're looking at phi VC of what, 16 kips? Half of phi VC of 8 kips? What equation do I need to use, 1 or 2? 2, right? But we're talking about shear values right here, right? And right here, we're talking about, you know, a shear of 16 kips probably going to be somewhere about like right there. About like right there. Make sense? So what we need to do is use this second equation. Now what I need to do is take this second equation and solve for x, right? So how do I solve? I take, let's see, take this, bring that over, divide by -4, right? And rearrange my signs a little bit. I can say it's 48 minus the shear divided by 4, right? So that's just algebra. So I propose that, that for the x value at phi VC, it's going to be 48 kips minus what phi VC is, 16.432 divided by 4. And all that is taking this lower equation, setting that equal to our shear of interest, and solving for x. That's it. And then this next one would be 48 kips minus 8.216 as follows. So you're going to get, let's see, 7.892 for the top one, which is going to be feet. So expand that out, you're going to get 94.7 inches. And then this one, what is it, 9.46, which is all right. I know it's been a while since we've done shear diagrams, like really done them, but I know you've done this before because I did it with you. So you tell me, is it so far so good? Are we doing all right? Any questions? Can we hold this up here for a second, or is everybody good? Okay. So now let's draw our shear diagram for real. Okay. All right. Now, I'm not going to use my straight edges and what have you, bless you. But just bear with me before you start drawing this out. So, okay. Now, what did our shear diagram look like before? It went, let's say, if went down like this, it went down, and it went like that, right? Something about like that. I know my scale's a little off, but you all have straight edges. You can fix that. Now, first thing that we do is we say, all right, let's take this shear diagram and let's cut it off some, which that is not a straight. That's going to bug me. All right, so we'll take this and we'll cut that off. So technically, the shear diagram extends all the way up to 68 kips. So this is my shear, or we'll say this is in kips, and this is my x distance in inches, right? All right. Now, technically, this extends all the way up to 68 inches. However, what we're allowed to use for design is this 61.333, and that's VU star. Okay? Maybe I'll erase that out a little bit, do that a little better. That's a little better. Okay, now that occurs at where? 20 inches, right? Make sense? Okay. We then reach, okay, this is 44. This is 24. And then we've now also got, what, this value right here. This is our 16.432, which is VVC, and that occurs at what? 94.7 inches. And then that's 119.4 inches, and that is half of PVC, and this is, was it 8.216? All right. Do you all see how we did that? Everybody good? Looking forward to lab. Is that what it is? All right. So I want to identify. Now here, let me start dimensioning some things. Now first off, this point right here at the very bottom, this is at 144 inches, right? Because this that's the center line of the beam, right? Because this shear diagram is going to be flipped over, and that's going to be the other half of it, right? So remember, we have three regions of interest. We've got this region here, and the rest. So maybe I'll extend this up a little bit so I'm not intruding into the rest of the diagram. So this region, I'll move that a little bit. This region. Okay. So this first region here on the left is anywhere that the shear is higher than this value right here, which is PVC. So this is where the concrete carries the shear. Okay? This next region, or no, sorry. I've labeled that incorrectly. I apologize. This is where the concrete carries the shear. This is the region where stirrups are required. Y'all should have corrected me on that. All right. This region here on the right, what's going on there? Well, it's where the shear is less than this. It's where we don't need stirrups at all. So, no stirrups needed. So, does that make sense? All right. Sound good? Any questions? All right. Now, instead of doing like 6 different designs like we did for our last problem, we're just going to do one and call it, okay? To sort of, put this example to bed, if you will. You missed your chance. All right, is everybody good? Everybody have this? Well, that was the second, so I'm moving on. Okay. All right. Can I move on? All right. You're going to want to refer to this here in a little bit, so keep this in mind, okay? All right. Okay, so now that we've, bless you, now that we've got our shear diagram, let's start to begin our design. So, 2, starting S value. Okay, so starting S value. Remember, we start our design based on VU star. So, we say basically just take that very first point on the shear diagram and say what stirrup spacing do we need to achieve that design. And we plug and chug. What's phi? And then 0.22, 60 KSI. D is 20 inches. Let me turn that up a little bit. 20 inches. And then we're looking at that first value on the shear diagram, so we use the 61.333 minus, what's PVC? We already computed that. There we go. So if you plug and chug, you're going to get what? Make y'all do some math. Okay. 4.41. So, you going to tell a contractor or a fabricator to use 4.41 inches of service spacing? No. So what are you going to tell them? 4 inches. Okay. Okay. So, I guess that's a little deceptive to say starting S value. We're going to put our first stirrup at 2 inches. Then we're going to use 4-inch spacing up until we can use our maximum S value. So let's look at our maximum S value. All right. So remember, we've got two ranges for S max. We've got S max 1. Which is the minimum of D over 2, or 24 inches. Which is going to be what? 10 inches. All right. Now for S max 2. We start off by computing 0.75 square root of FC prime. And we get that. Remember, we take that denominator to be the maximum of either this or 50. So we're just going to use the 50. All right? So therefore, and plug and chug, and that gives you 26.4 inches. I went a little fast, but is everybody okay with this? I mean, you tell me. This is literally the same process we used on the last problem. Oh, sorry. I have it here written, and I just didn't do it. I'm sorry. I am glad to see that someone is paying attention. This is right. I mean, check me if you don't believe me, but that's right. I'm sitting looking right at it. So of these two values, which one are we going to use? We've got an S max 1 and an S max 2, 10 inches. So now we've got, oh, getting ahead of myself. All right. Okay. All right. Is everybody with me so far? Let's keep our eye on the prize. So let's think about our design. We're going to start off with, here's our beam. We'll say, here's our beam, looking at this table. We're going to start off putting our first stirrup at 2 inches. Then we're going to use 4-inch spacing until we can start using this. Now, we know we can start using 4-inch spacing right at the very beginning. Maybe we need to figure out when we can start using 10 inches. Make sense? So let's, for step 4, we're going to find something kind of interesting. This is where you got to use your noggin and pay attention. Determine the range for S equals 10 inches. So basically what I'm going to do is I'm going to say, let's assume S equals 10 inches. Let's compute the capacity and figure out where that is on the shear diagram. Does that make sense? Okay. So start off, compute VS. And what is that? Okay. Then now we can compute VVN, right? What's VVC? What do we get? Sound good? All right. Think about this for a second. Okay, so I'm trying to determine where on the shear diagram this occurs. So I've got these two equations, right? Which one do I use? It's a trick question. Neither. Why? There you go. Look at this. Let's go back a panel. I'm trying to figure out where on the shear diagram VVN occurs. What is VVN? Like 36 something? It's right there. And where is that? Where is this point? Right here. No. It's all about using your noggin. So therefore, no, it's not always going to appear. That was a coincidence. Make sense? All right. Can I go on to the next panel? Well, I am. No, do you need me to? Oh, okay. Okay. I'm going to verbally write out what we've got to do. So, start, yes? Right here. It's right there. The drop occurs right here. That's 6 foot. That's a good question. Yes. Because 6 times 12 is 72. All right. So here's my design. I'm going to start first stirrup at 2 inches. And then we're going to go a couple minutes. So start the first stirrup at 2 inches. Then we're going to use 4-inch spacing until when? Then we're going to use 12-inch spacing until x equals what? $119.4. So, first one. Right. Oh, 10. Thank you. All right. Okay, so I placed my first stirrup at 2 inches. Okay. Then my next increment is 4 inches. Okay. Now, I can use that until x equals 72 feet. So I've traversed 2. That means I've got 70 left, right? What is 70 divided by 4? 17 and a half. That means I need to use 18 stirrups at 4 inches, which is going to be 72. Okay? Now I'm allowed to use 10-inch spacing. Now, how much of the beam have I traversed? I've traversed 74, right? So what's this minus 74? This minus 74. Say it again. 45.4. Using 10-inch spacing, how many increments do I need? 5. Okay. So 2 and 72 is 74. 50, that's 124. And then 119, 5, 24 stirrups. If you decide to throw an extra increment in the spacing, you can shave off like about 2 stirrups total for this problem, but that might be debatable, you know, for economy standpoint. We're not quite done. Now, technically, you should check that V sub S equals 4 lambda squared of, or lambda BWD squared of FC prime, but that arguably won't be an issue. In the meantime, I do have a gift for you. All right. You all need to pay attention to what I'm about to say for this homework so that you all understand. So on Problems 2 and 3, I've sort of given you all some dictation in terms of how you're supposed to design it. So for problem 2 and 3, don't worry about moving loads or anything like that. It'll say that in the problem. I ain't worried about that. Begin your first stirrup at 2 inches, regardless of what you do. And I want you to use at most 2 increments of spacing. The stirrup spacing at x equals d, or VU star, and the maximum allowable. So don't do any stirrup increments in between. You do that, we should all arrive at the same answer. So that's to QAQC the homework. Everybody good? Do Wednesday when you get back. It's not due on Monday. All right, guys. You all have a great spring break. I will see you all when you get back. Hold on.